It's an honor for me to be here, and I thank the organizing committee and University Paulista for inviting me. It's not my first time in Brazil, but every time is exciting. And so I really enjoy to be here with you, and I hope to give some small contribution to the common work. I fully agree with Professor Huizing said about a workshop. We are here to work together. So we will spend 3 very intensive days sharing our knowledge and sharing our expectations. And for sure, we will get somewhere. We will be productive, and I look forward to the next special issue of Cleaner Production. And thanks, Don, for doing this so well. And thanks to all the other organizers for this effort. I know that it's a huge effort. I have been the organizer of another series of workshops, Advances in Energy Production, which was very hard to put together and to continue. And this is the reason it's going to be held in India next year and not in Italy. It will be in Mumbai University, so I will take a rest. Well, let's start. If you have nothing against, I will sit. Is it coming? Good. Good. So you see the volcano. I see the volcano from my window. It is expected is one of the most studied volcanoes in the world. We have a lot of visiting professors coming to monitor the activity of this volcano and see and be there when he will erupt to study the event. I hope I will not be there. I hope to be somewhere else. Anyway, yes, the title is very long, and I hope the presentation will not be that long and that difficult as the title is. But you know Italians, we talk a lot. And so, before I start, I would like to acknowledge the contribution of some people who supported me putting together the content. All of them, Francesco Cherubini, Sandra Fad, Salvatore Mellino, and Gabriella Fiorentino, are my previous PhD students, and they are now, some of them work with me, and some emigrated to find a job somewhere else, and none of them is older than 30 years. You know that tale, the story, you cannot teach new tricks to an old dog. This is something that is not for professors close to retirement as I am, but it's for the young people. You are here, we expect from many of the young people in this room and in our universities to perform the job of leading us towards a society that is no longer based on fossil fuels and is cleaner and is more renewable. I really acknowledge the work of these ex-students in my activity, and I am fully supported by them, also in the speech I'm giving. So let's start with a problem that we have to solve. Us, we are the problem. Can you read it? Yes. All studies identify our activities as a primary cause of the Earth system crisis. We are the problem that generates pollution, etc. The 20th century has seen exponential growth in human populations made possible by the industrial scale exploitation of natural resources and services. I was a student at university when the Danella Meadows report on the state of the world to the Club of Rome came out. We were 3.5 billion at that time, and everybody was crazy. Oh, we are going to be too many. Actually, now we are 7 billion. And we are trying to make it. We're trying to solve how to ensure to the 7 billion people a dignitous life based on renewables. The globalized industrial economy is committed to continued growth in production and consumption. This is what we face every day. And unfortunately, growth demands ever-increasing energy and material inputs. And we are in a limited world. So that growth results in increasing levels of pollution, resource depletion, species loss, and ecosystem degradation. This is the problem we are facing. This is why we are here. And many studies, this can be seen, many studies reported growth of population, GDP, investments, and fertilizer consumption, and water use, and river damming, and even increase of McDonald's restaurants everywhere in the world, and paper consumption, which means cutting forests, clearing forests, etc. And all of this had an effect, and the effect was global scale changes in Earth systems as a result of our activity. So we release CO2, we release sulfur, we deplete the ozone layer, and more, and we degrade the ecosystem by simplifying the number of species. And of course, we should stop this trend, we should do something, and this is the real challenge we are facing. So the problem is business as usual. The people who advocate business as usual suggest that the only problem is finding new energy. We need more energy to support a growing economy, so we need deeper reservoirs, nuclear, oil sands, and new land to exploit, new mineral reservoirs to dig. This is the basis for business as usual economy. And we are addicted to energy, mainly to fossil energy. This is our problem. The advocates of business as usual growth disregard the declining net return of energy sources, which means that it takes more efforts to get the same results now because the best reservoirs have been exploited. And so now we have to invest more to get the same result. And investing more means less net energy and more environmental stress. Business as usual is not an option for the future of our planet. Because unlimited growth is impossible in a limited planet, and we are already constrained by many limits. The limits to growth, the limits to exploitation. And this guy on the boat says, he denies that economic growth cannot be pushed forever, and he invites the people to do something, and he says, what the hell is wrong with you people? Row. You want all of us to drown? So, all of us means the economy that is based on business usual. We may change the economy, we may change something of our economic activities and survive. Some of you know this guy, Howard Odum. He was my mentor at the University of Florida. He pointed out the impossibility of business as usual and the search for alternatives, the need to search for alternatives. He used to say that we must plan ahead, because planning ahead makes the difference between a soft landing and a crash. We don't want to have any crash. We would like to have a future that is prosperous. And this is why he wrote his last book, A Prosperous Way Down, Principles and Policies, advocating that there are alternatives, not for growth, but for prosperity, which is different than growth. He developed a pulsing model in which he identified 4 stages in the growth cycle, and there is a stage in which we grow, then there is a kind of climax in which we use the resources in a very efficient way, and then there is a descent in which resources are declining and we have to change our attitudes. We must find a way to get more out of less. And then finally, there will be a stage of low restoration of resources with no growth. And these are cycles in the history of the humanity. We had a cycle which was the Roman Empire, for instance, in Europe, and then other cycles up to now. And we already see that that something is changing even now in the economy of the 20th century. Policies that were good, economic instruments that were good in times of growth are no longer appropriate in times of climax or descent. We have to find new policies. We have to develop new economic instruments and theories that are no longer the neoclassical economics of business as usual, decoupled by the environment. And this is the real challenge for the next generations. No matter we cut the oil consumption, the hydrocarbon age is over, is almost over. For sure, the cheap age of fossil fuels is over. Oil is now at about $100 per barrel and keeps growing. Some speculation helps. Some political reason is helping pushing the oil up. But there is, for sure, there is a peak of oil. The production of oil every day is shrinking because the best reservoirs are being depleted. We know this, and there is nothing we can do. We must get out of the oil age before it's too late. We must use the last oil that is left, the last cheap oil that is left, to get out of this. And those people who believe that we can use the nuclear must be aware that there is also a peak of uranium. The amount of uranium is limited, and the nuclear association, the ones who work in uranium and nuclear power plants, say that there is uranium at $30, $40 per kilogram for 80 years. Then there will be a limited amount of uranium at higher prices, up to $130 per kilogram, and then that's it. After 100 years, there will be no uranium at the present consumption. If consumption increases, it will be even shorter. So we cannot expect non-renewable sources to support our new economy. And the reason is that to get resources, we must invest. And the investment must be rewarding. We must have a net energy out of the investment. We invest 1, we must get 2. And we must have an energy return. There is an indicator that was developed by Kaufman, Cleveland, Charlie Hall, and others. And this energy return on investment that may help us to see how energy sources and how materials can support a developed society. For instance, oil. Oil used to be very cheap and very easy to extract in the past. You made a small hole and you could extract easily oil because oil was in the surface. And now oil is deeper, and we must look for oil in the oceans, undersea, and it's not easy. It requires huge investment. And the ROI of refined fuels now, after petroleum recovery, transportation, petroleum refining expenses, gasoline transportation, and finally is 5:1. This means that we invest 1 joule and we get 5 in the form of refined fuels. It's still good. In the past was 20:1, 15:1, 10:1, and now it's only 5:1. This means that the age of oil being able to support our luxury is very close to the end. But on the other side, if we need to replace oil, we need to find sources that can support, that can have this return, 5:1 or more. If we find sources with less than this, it will be a problem. Let's show this with the diagram. Yeah. I may need a pointer here. Okay. The 4 columns are assumptions that we made for Italy. Italy in the year 2005 used 200 million tons of oil equivalent. Assume that we can support this consumption based on 20:1 ROI. So you invest 1 joule, you get 20. So we had to invest only 10 million tons of oil equivalent per year to get 190, more or less. And due to the entropy law and inefficiencies, we would have a loss of 60, more or less 60 million tons of oil equivalent, and so the net would be only 122. This 122 supports the Italian economy, means the service sector, transportation, heating systems, etc., etc. Now, 5:1 ROA means that we invest more and we get less. Now is the present situation. And the present situation means that we have a net of only 104. What would happen if we had only 2:1? No, so invest 1, get 2. A very bad fuel. This would be bioethanol from corn, for instance. We have to invest 88, some inefficiency, and we get only 71 net. We cannot support the same society based on 71. We'll have a smaller economic activity or maybe a more efficient. So, but for sure, this is the problem. And if we have even worse ratio, return, the investment would be largely over any possibility of supporting a developed society. What happened now? That due to the economic crisis, some economy of Italy shrinked, and we have been forced to become a little bit more efficient, and now we consume only 170 million ton oil equivalent. In 5 years, we had to do this. And part of this was not good, means that the economy is not going well, okay? And so what we did some change in the mix of energy sources, shifting to methane, from oil to methane, some renewables, and now we are in this situation in which we have a smaller investment due to the changed mix. We are investing in gas that is easier to get. And less inefficiencies thanks to improved systems, to awareness that we must become more efficient, and therefore we still have more or less the same amount of net oil, net energy, which allows the economy of Italy to be still there. What's the meaning of this? The meaning is that if we become more efficient, if we look for another source that has the same return, we can still support the economy based on a smaller amount of energy available. But what are the alternatives now? We should have to get out of the fossil fuels. No doubt on this. But electricity and heat can still be provided by a variety of renewable alternatives. For instance, we could have photovoltaic electricity, use it directly, or electrolyzing the water and get hydrogen, liquid hydrogen as a fuel for transportation. But there are the majority of the fuels and chemicals and materials must be produced, will have to be produced from biomass. Because biomass is the only source alternative to fossil fuels that is still carbon rich. I don't know, I cannot say how long will it take to shift from fossil fuels to a biomass-based society, and I know that it will be difficult, and it will take a lot of research activity, but it's the only option that we have. Alternatives must be environmentally friendly, less or no loading at all on water, land, air, climate, and biodiversity. So we're asking a lot. Must be renewable. The age of fossil fuel is over. Must be complex and integrated. All components of a system, of an economic system, must interact, must exchange energy and matter flows in order to decrease emissions and waste. The word waste must disappear. Must be aiming at well-being, not at pure growth, economic growth. We must be better off, but being better off doesn't mean having only new commodities. And we must be sustainable under different points of view: energetic, environmental, economic, and social. To make it clear what I mean, you may have heard that some companies have suggested to make biofuel production by cropping the contaminated land in Belarus around the Chernobyl nuclear power plant. One of these companies was an Irish company, the Greenfield Project Management Limited. They announced in 2009 that they were ready to crop 40 million hectares of land, 1/6 of Sweden. And it was a false announcement. They only did to raise money, and then now they are in bankruptcy, and all the managers have been fired, luckily. But on 11th of May 2011, so 2 days ago, another announcement came from Photofuels, a Belgian-Ukrainian joint venture, and they got the permit from the Ukrainian government to test new crops in the polluted area to make biofuels to sell in Europe. Okay, our alternative cannot be this. This is something that is even more scary than the running out of oil. So the alternative must be somewhere else. And many of us are now aware that the alternative cannot be generating fuel from food crops. Corn, wheat, oilseeds. It was a failure. The investment, they have no high yield. The investment is huge. They need good arable land, and it didn't work. Because you need an agricultural phase to produce the biomass. The biomass is not high yield. You need a conversion step. You need to leave some residues in the field. You need to use some residues in the process. You need to feed back the agricultural phase, which is very energy intensive, especially talking about corn, and the net you get is very small. It is 1.3 to 1. You invest 1 joule and we get 1.3. There is no way to support a developed society on this. We did other tests. We evaluated many different alternatives. One that we evaluated was in China, and the result was from wheat, 1.09. You invest 1 joule and you get 1.09. You get another joule. So it's not a fuel alternative. From corn was 1.19. Same, is a failure. Using an energy-based indicator, energy is a measure of the demand for environmental support of a product, how much work of nature, the sun, the wind, the rain, the microorganisms, work for the development of an alternative to generate resources. And the demand for environmental support measured in solar equivalent joules per joule of product was 2.77 10 to 5, which is twice the same value of fossil fuels. These fuels from food are 50% less renewable than fossil fuels. It is not an alternative. We cannot rely on this. And so the second generation has been proposed. What is second generation? Well, first generation is deriving fuel from food crops. And the major issues is that we need the crops, which means we cannot eat them. There is a competition, food versus fuel, water demand, many environmental issues, land clearing, and soil degradation. So, what is the difference with second generation biofuels? That is based on lignocellulosic materials, which is a very abundant substrate. When we produce corn, we also have straw. When we produce wheat, we also have straw. Many non-food crops can be generated with high yield and less intensive cropping systems. There are several conversion technologies, hydrolysis, fermentation, gasification, and pyrolysis, that are now very close to the commercial stage. And therefore, and more, we can utilize waste materials, waste paper, paper mill waste, wood waste, urban waste, and agricultural crop residues. So the hope is that this very abundant material can provide the substrate for biofuels, cheaper biofuels, and more than that, biochemicals. 90% of the biochemicals we use are made from fossil fuels. Can you imagine when we run out of fossil fuels or when they become more expensive, everything will disappear. This is made with fossil fuels. And so also this. And so we have to find alternatives. And that's it. Biomass is more important as a source of biochemicals than as a source of energy. Well, I will skip this. What is a biorefinery now? The definition is the sustainable processing of biomass into a spectrum of marketable products and energy. Marketable products, products that can be the basis of a new economy. This is the International Energy Agency definition. Many different kinds of biomass, crops, wood, waste, and non-food crops that are the basis of the biorefinery concept, a wide range of different technologies that separate the biomass into components in building blocks that are carbohydrates, proteins, biogas, and fats, and then convert them into value-added products, biofuels, and chemicals. This is the goal. So it's a challenge, and we are not yet there, but we are getting closer. So in short, there will be different, there will be a kind of biomass pre-treated, shredded, cut in pieces, and steam exploded, and then converted into smaller components and polymers, and then converted to biomaterial, bioenergy, and biochemicals. Seems simple. It's not that simple, but is the solution. So we have After the first pretreatment is done, we have some intermediate products. Platform is a jargon word to mean intermediate products, building blocks, and will be sugars, will be syngas, which is a mix of hydrogen and carbon monoxide, and methane, and biogas, which is more or less methane, and carbon-rich chain, which is the oil from oilseed crops. So this is what we have, and we have conversion technologies to make products out of that. These conversion technologies are very close to large-scale production, so we can invest in them. The building blocks, lignocellulosic materials, are composed by cellulose, a very difficult to hydrolyze product, component, 30%, hemicellulose that are easier and that are composed with hexoses and pentoses, so sugars that can be easily fermented. And the most difficult thing is the lignin, which is a polymer of phenols, which cannot be fermented, are very hard to be separated from cellulose and hemicellulose, and are the support structure of the plants. So the issue is separating the three components, then hydrolyzing them, then converting them into a variety of chemical products. For instance, one of the most important is the number 5 here, the levulinic acid that is generated out of hexoses and pentoses, and is the basis of the so-called green chemistry. Also furfural, number 3 here, is another important component. We can convert these products into, after having hydrolyzed the cellulose and the hemicellulose, and having extracted 6 carbon sugars and 5 carbon sugars, now we have to convert them into furfural and levulinic acid and a variety of fuel additives, resins, plastic materials, and all the needed chemicals. For instance, here is the furfural. And from the furfural, you can get the levulinic acid and a variety of other products. For instance, nylon here, and many other components that fumaric acid that are used for herbicides, for resins, and as fuel additives. All the plastics, all the fossil fuel-based plastic that we have can be replaced by this biomass-based chemistry. And after you have the levulinic acid, you move to another series of products. I cannot go into this. You can make fuel additives and all kinds of plastic materials and intermediates that will replace the ones that we use to make from fossil fuels. So now the question is this feasible? What should we do? First of all, we have to identify the substrates, the intermediate products, and the technological pathways to be followed. And this means some substrates are already well known. Starch, for instance, can be converted into monosaccharides, so into sugars, and from sugars fermented to ethanol and animal feed. Oil crops can be converted into triglycerides, and then oil, and then biodiesel, and other chemicals. And organic residues can be fermented in an anaerobic digester and give rise to biogas and fertilizers. So there are already well-known chains, and lignocellulosic materials will be gasified, can be gasified and become syngas and from syngas, they can be still converted into hydrogen and other chemicals. And more, grasses will be the basis for the so-named green biorefinery, getting organic juice from which proteins and amino acids can be extracted, and then more fertilizers and biogas. And finally, we can convert lignocellulosic materials also through the pyrolysis and get other fuels as transportation. And finally, the well-known sugar crops, as you do in Brazil with sugarcane, become bioethanol. So we have a large set of products that can be made out of those substrates here and through a lot of intermediate products and technologies. This is the future that we are working for. The European Union is investing a huge amount of money through this to go from first-generation fuels that didn't work, but they allowed to gain knowledge on the process. So it was good from the point of view of research. Through second generation and then to integrated biorefinery complex. That is the goal. When I say biorefinery, I'm not saying a big plant. People, especially in Italy, as soon as they see a big plant, start being scared, what's going to happen, another source of pollution. It's a network. It's a network of smaller activities that exchange matter and energy. So the step 2 is designing an integrated system. So we know what are the technologies, we know that we have the substrates, so now we have to design a system. This is the one that we are trying to do in my region, around Naples, with the help of the farmer associations and the business community. We have several activities that become the source of the substrate, olive farms, vineyard farms, they are very many in the region, and tomato production, fruit production, forest management, grassland and fodder farms, and marginal land. We are focusing more on marginal land, and I will say something about this. Through a series of conversion, we have the main product. Olive mill generates oil for the market. Winery generates wine for the market. But also, you have tomatoes and processed food for the market, etc. But also, we can extract many chemicals out of the residues and waste of these activities and deliver them to the chemical industry to make pharmaceutical products, to make cosmetic products, to make food integrators, and also we can deliver the residues of the residues to digesters, to boilers, and to gasifiers, and make electricity and heat. And they, in turn, are fed back to the system. From here, they go back as fertilizers and as electricity to the system to make the system independent. What is important is this integrated system cannot hope to be supported by fossil fuels because sooner or later we run out. They must be self-sufficient. And this is what are we doing there. Step 3, is this really profitable? Assessing, are they really environmental friendly? And so we applied LCA, life cycle assessment, to some of this patterns. Well, I skipped the definition, life cycle assessment. Okay, this will be from wood residues. Okay, wood can undergo natural decomposition and become part of the soil, organic matter. We must leave some wood in the soil because the organic matter is important. But we can also collect the wood and make transport the wood, process the wood, and make a biorefinery plant or network. I like better biorefinery network, and generate biofuels, heat, electricity, and chemicals and hydrogen, distribute it as products and services. And we compared this with the same system and the same products that are electricity, chemicals, heat, and gasoline, the same products and services from natural gas and from oil, to see what is more effective in terms of environmental protection. Okay, skip this scheme. Okay, this is hard to read, but here is the biorefinery system that generates a service of transportation, a given number of million kilometers of transportation, in the form of bioethanol and methyl tetrahydrofurane, that is another, that comes from levulinic acid chemistry. And then some resins that are used for plastics, some fumaric acid, and electricity, and heat, and biomethane, and hydrogen, and fertilizers. These are from the products of a biorefinery. So the goal is compare does it cost to make this, and how is to make from fossil fuels. Fossil fuels is here, gasoline for transportation. This number is the sum of these two. The other ones are the same because the comparison must be done on the same basis. The greenhouse gas emissions are from fossil fuels, 336,000 tons of CO2 equivalents per year in this plant that we have simulated, versus 36 kilotons. So it's 10 times less, and the CO2 emissions only are much less. The primary energy demand is higher for the bio-based materials, but this is only a very small amount is from fossil. The other one is solar energy, while it is 4,000 terawatt. What is that? Terawatt hours. Should have been an H there. Anyway, so it's joule. I cannot read this, my eyes. Terajoules per year. What happens? So, okay. Okay, it came out. It seems I have no power here. And that's, anyway. Okay, this is a very high amount of fossil energy. In turn, this fossil energy will generate greenhouse gas emissions. In terms of greenhouse gas emissions saved with the biorefinery, will be the difference between this and this will be 300 kiloton of CO2 equivalents, and a lot of energy saved, including or excluding credits for the energy for the heat production. So this biorefinery based on wood is very much productive, and the greenhouse release are the difference between the columns on the right and the column on the left. These are the greenhouse gases, CO2, N2O, and methane. Is really huge. We did the same for corn stover and wheat straw, the same evaluation. Consider we're doing with the residues, not the main crop. I'm not going through the results of this, but we got the same good results because the same kind of services cost much less through the biorefinery system, and they provide an additional income to the farm. They are the basis for a bio-based agro-industry that has nothing to do with food production. It does not compete with food production. And so, okay, for instance, this is the fossil reference system, energy demand, and this is the energy demand to produce the wheat straw and the corn stover and make biochemicals and run the biorefinery. So there is really a huge difference. This cannot be seen easily, but you see just one. For instance, the contribution to global warming from a biorefinery based on corn stover will be 137 kilotons CO2 per year, and for the fossil reference system is 296. And the same for all the other LCA impact assessment categories. So, when you perform a multi-dimensional assessment that is all based on energy demand, greenhouse gas emissions, abiotic material demand, etc., all the indicators are much better for the biorefinery than for the fossil reference system. So step number 4, expanding the focus, is just biophysical indicators, but how about the economic? How about the time needed for resource replacement? And therefore we developed another extended LCA approach that we named SUMMA, Sustainability Multi-Scale, Multi-Method Approach, which is an LCA with the addition of process efficiency evaluation, which is the exergy method, environmental support evaluation, which is the emergy method, the one developed by Howard Odum, and which includes economic assessment and embodied time, the time needed for resource generation. When the assessment is done, we have many different kinds of flows, mass flows, energy flows, free environmental flows from nature, wind, rain, etc., and economic flows and money flows, and they give rise to a variety of indicators that are indicators of material demand, abiotic material demand, of embodied energy demand, exergy efficiency, and emergy investment. And finally, there are socioeconomics indicators needed too, that are emergy per hectare, emergy per euro of income generated, etc. All these indicators allow an upstream and downstream assessment of the performance, so it's a very complete picture, after which you can say it's profitable from many different points of view. And this is what we did in our region. Focusing on the last case study, we involved also geographical information system to evaluate if we can use non-food crops on land that is no longer suitable for agriculture, polluted land, marginal, not irrigated land. What we did is comparing cropping for energy and cropping for biorefinery. This is my region, Campania region. Thank you, I will make it. You see that we have the green part is forest, the brown part is agricultural areas, the red one is cities. And the colored areas here are the polluted land from previous industrial activities or from previous illegal storage of, disposal of chemicals. And therefore, we overlaid these two things, and we have this land that is polluted, and also these two levels that are really unsuitable for food. And within the polluted area, we have also some areas that are not irrigated, cannot be irrigated for many reasons, and we simulated the production of biochemicals and biofuels in these areas here, 40,000 hectares, and to see if they were feasible or not. The crop was Ethiopian mustard. Brassica carinata is an oilseed crop, which doesn't require, grows very well in semi-arid areas, has low water requirement, doesn't need many fertilizers, etc. Is a good crop, non-food crop. We did the two cases based on real experimental plots. One of the members of the team was an agronomic engineer. We did the actual cropping system, and we used for the simulation the real results of hectares cropped. So, two different ways. Sorry, it's going too fast. One is making oil, biodiesel, and glycerin, and then burning all the agricultural residues to make heat, and use the heat to replace fossil fuels. And this delivered net energy per hectare of this amount. Low input means not intensive agriculture. High input means intensive agriculture. We got this, but multiplying this per hectare energy times all the hectares available provided an amount of oil that was only 10% and 13% of the total energy used in agriculture, so it's not that much. And the real problem was that the economic investment was too big, because anyway you had to pay labor for this. If you crop for energy, you need to pay. And it took 4 times more money than we saved. And so this alternative provides some energy, but is unfeasible from an economic point of view. Very quickly, the other alternative was the biofine process, which is using two hydrolysis reactor to convert the lignocellulose into monomers and make chemicals instead of energy, and saving energy from fossil fuel for not making the chemicals, and generating levulinic, formic acid, furfural, and char. And char has also huge caloric value. And using this to produce specialty chemicals, commodity chemicals, herbicides, automotive fuels, and energy. Yeah. And so there was an income from doing this, much higher than for the energy, and the result is that the reward is higher net and more money, 2 times more money than invested. So this can support an economy and provides an energy saving. Well, I will go just on this figure. This is the fossil fuel route to make these products that are resins, urea, nylon, etc. It takes more than 3 times the energy content of these plastics, while instead doing the same, for instance, the levulinic in the biorefinery requires less than the energy content of 1 gram of fossil fuels. Look at the difference. 1 gram of fossil fuels is 42 gigajoule per ton. And to make the plastics, the fossil-based chemicals requires more than twice this much. This is the reference line. Instead, if you do this in a biorefinery system, this is 32 gigajoule per ton equivalent, so it's less than the energy content of 1 gram of fossil fuel. So this is much more rewarding. So my concluding remarks is that we will have to rely on biomass for liquid fuels, chemicals and materials when we run out of cheap fossil fuels. No doubt on this. I cannot say when, but it's not that far. Cropping for energy, even in marginal land, is never an option, only energy. Apart from some Brazilian sugarcane in some cases, due to the low energy return and high cost. Cost means processing cost and agricultural cost. Instead of expensive cropping for energy, the use of waste lignocellulose residues provides interesting substrate abundant and low cost and energy self-sufficient alternative, which is the biorefinery. The concept of biorefinery solves the problem of agro-industrial and urban waste, promises cheap liquid fuels and biomaterial and biochemicals. And biochemicals can be already produced at competitive cost with petrochemicals, competitive compared to petrochemicals. Bioenergy is more difficult, only bioenergy, because of low hydrolysis yields. Some high yields processed biofine are very close to commercial stage. I would like to say that the first commercial plant that does levulinic acid in the world has been made in Campania region. It worked from 2005 to 2007, generating very cheap and cost-effective biochemicals. Now, due to budget reasons, stopped the activity, but is expected to start again very soon. Linear cellulose is everywhere and therefore contributes to the independence from fossil fuels. This is the challenge, and this is what we should work on for a sustainable future. Thank you for your attention.